Okay, we've looked at expectations and functions of expectations. It also makes sense to talk about correlation and joint averages. So, in this case, averages, we want to know various things, but let's go ahead and define the general case and talk about what this might give us. So if we have two random variables, then we need to utilize the joint probability density function, or PDF, when taking our expectation. So it's a double integral, but often these two variables have nothing to do with each other. If they are independent, then we can factor this out into 2. So if they both factor, we say that these variables are independent. And so statistical independence implies that P, xn, ym, and I suppose I should have used m as the second variable above. I'll fix that. There we are. Of x, y is equal to pxn times p ym. Statistical independence. Now, you can have things that are not independent. Well, actually, first let's look at this. If we have statistical independence, that implies that the expected value of x, and of course we have to have a g that factors to do this, but it's not required for dependence. Ym is equal to the integral of g x p x x comma n dx times the integral of g of y py which, for looking at the product, xn, for example, times yn, means that we have expected value of xn times the expected value of ym. So, statistical independence essentially means that it manifests in that the expectation of the product is equal to the product of the expectations. It can take us further than that, but that's an important step. Now, it turns out that we can have this, that the expectation of the product is equal to the product of the expectations without statistical independence. So we're going to give this a separate name and distinguish it, and I'll show how this all fits together. So this is also, and I'll just put it down here on a separate line, xn ym equals expected value of xn ym. Then we say that x and y are uncorrelated. Now, this is important. Independence implies uncorrelated, but uncorrelated does not imply independence. So independence is a stronger condition. Now, I'll say this because it comes up. Often we work with signals that have zero mean. And the reason why is for some types of analysis, it just makes things a lot simpler. So if one of these signals had zero mean, that would imply that the expectation of the product would be zero if they're uncorrelated. Because of that, some people get in their minds that if the expectation of the product is zero, they're uncorrelated. And if it's not zero, they're not uncorrelated. That is not true. That's an artifact of dealing with zero mean signals, which is not the generality. So it's important to remember these definitions as we've discussed them. But as long as we've introduced this, let's talk about just a few other functions that are very important in many types of signal processing. One we call the autocorrelation function, and that's just equal to the expected value of xn times xm star. Similar to that is the autocovariance function. It's called auto because, look at this, we're operating on the same signal, just with different time indices. And as you might expect, this is the expected value with the mean removed. And since the variance is a function with mean removed. We often apply the moniker function at the end of this because we tend to calculate these as a function of n and m, as is shown over there. And then of course we have our cross functions, x, y, and m. So now we're dealing with different random sequences at different lags. And this would be our cross correlation. Not used as often. The autocorrelation is actually very useful, but this is used. It's just not quite as common in the things that I've seen as the auto functions. And this is our cross covariance function. So we'll find that the autocorrelation function is actually used a lot in prediction, and is used therefore in predictive coders such as speech coders. It's also used in analyzing the structure of a signal, and as such is used to give us the frequency content in random signals. So we'll see that quite a bit, but we'll save that for another day. Thank you.